So, first of all, so let's call this pH calculations. Does it work? Yeah. And I really want you to do these calculations together with me, because it gives you some good practice. Okay, so here is the first question. I have 1 milliliter of 1 molar HCl solution. And you can assume that HCl is a very strong acid. What is the pH? What is the pH of this thing? And you really don't even need a calculator. pH is?
0.
pH is 0. How did you do that?
This log, minus log, and the one will give you 0.
Okay, you are absolutely right. So pH equals negative log of the acid concentration, and we can assume that in this case the 1 molar concentration of the HCl completely dissociates and gives us 1 mole per liter of protons. So 1, and the assumption is that it is in molar. So log 1 is 0. We still have a negative, but with zeros it doesn't matter. So the pH equals 0. Well, that wasn't too difficult. Okay, now we take, by the way, what are we doing with this 1 milliliter? What are we doing with this 1 milliliter? Is this of importance here? We haven't used it really in our calculation. Does it matter? Somebody's grunting. Does it matter? No, it doesn't matter. Because the pH is totally independent of the volume in which we have the solution. It basically boils down to this guy here. What is our molarity of the protons? Okay. Here's another one. We have 100 milliliter of pure water. Somebody complained last time. What's the pH of pure water? Is water acidic? No. Is water basic? No. So it's in between. What's the pH? 7. Thank you. pH is 7. That's pure water. So now, we take 1 milliliter of a 1 molar HCl and put it into 100 milliliter of water. What is the pH in this case? We said this guy here is pH 0. This guy here is pH 7. Huh. It's an interesting question, isn't it? Could come up in an exam. Sorry. How are we going to address this question? Well, we know that pH equals negative log of the proton concentration. Right? And what is a concentration? Concentration is simply moles of the protons per liter, or simply an amount per volume. So what is our total volume that we have? If you look at that, what is our total volume? See? 101 milliliter. Exactly, it's 101 milliliter, isn't it? Because we add 1 milliliter to 100 milliliter. So our volume is 101 milliliter. Absolutely right. What is the amount of moles that we have? Moles of protons that we have. Can we figure that out? Well, we can figure it out. We know that we have 1 milliliter of a 1 molar acid solution. So we could say here, let me do that in a different color, mole of protons equals 1 mole per liter. That's this one here. So we want the moles, that's the right one. But we need to get rid of the liters. So how many moles do we have in this 1 milliliter? So we do it 1 mole per liter times 1 times 10 to the minus 3 liter. That is this guy here. And we use this because our protons come from the acid. So we want to know how many moles do we have in this 1 milliliter of the hydrochloric acid. And if we do that, if we do this calculation, we get, well, the liters cancel out, and we get 1 times 10 to the minus 3 mole. So 1 times 10 to the minus 3 mole. So we have 1 times 10 to the minus 3 mole in our 1 milliliter. And that indeed is our proton concentration. 1 times 10 to the minus 3 mole. Okay? Happy with that? Now, we can write now for our concentration, we can write we have minus log of 1 times 10 to the minus 3 divided by 0.101. Remember, we always need to have mole per liter, and instead of 101, Dalmatians, 101 milliliter, I can write 0.101 liter. You still with me? So we have pH equals minus log of 1 times 10 to the minus 3, 1 times 10 to the minus 3 divided by 0.101 gives me minus log roughly 1 times 10 to the minus 2. Is that right? What is log 1 times 10 to the minus 2? 2. Minus? Yeah. Minus negative 2. So the pH of this equals 2. So did you see how it's done? First, we need to ask how many moles of protons do we actually have in our acid? What is the volume that we have? And that gives us the concentration of our protons. Okay? So, what we can say is we have 1 molar HCl. This has a pH of 0. We have water that has a pH of 7. And if we combine this, in this particular case, 1 milliliter, 100 milliliter, the solution has a pH of 2. Happy with that? Yeah? Okay. So, hydrochloric acid is a very strong acid. That's why we have a pH of 0. Beautiful. A blind person would be so glad to see that. Okay, let's do a similar thing. We have 1 milliliter of 1 molar solution of an acid. I just called it HA. But this time, the acid is weak. And we said a weak acid, we usually know because usually we are given a pKa value. pKa value tells you how much this acid actually dissociates, how much it falls apart. And we said the higher the pKa value, the weaker the acid. And in this case, the pKa should be 5. So, first of all, let's calculate what is the pH of this HA solution. And I gave you the equation last time. pH equals 1/2 of pKa minus log of the HA. Remember? You would need to learn this equation for the exams and for tests, because I think it's quite an important equation. I won't give it to you in an extra sheet. It's not terribly difficult to learn this equation, I guess. So let's do our little calculation. pH equals 1/2 of pKa, in this case is 5, minus log of the acid concentration, and that was 1. So, log 1 gives us 0. 5 take away 0 is still 0, is still 5. So we have 1/2 of 5 minus 0, and that gives us 2.5. Okay, happy with that? So the pH of this weak acid is 2.5. Remember, the pH of our hydrochloric acid was 0 under these conditions. Which one is the stronger acid? HCl or HA? HCl is the stronger acid. Which one would you be happy to stick your finger in? In HA, yeah. I've done the experiment with both myself, HA and HCl, and I can tell you HCl, it bloody hurts. And you can feel the skin of your finger slowly disappearing. It's not very nice. And especially if you have little paper cuts. Wow! You feel that you are alive because you can feel the pain. Actually, pH 2.5 is pretty much what you get with pure vinegar. That's the stuff that you put on your chips. So you eat pH 2.5. pH 1, high up the scale, is what you've got in your stomach, with the hydrochloric acid in your stomach. Just to give you a sort of a relationship. So, we've calculated the pH of this fairly weak acid, pH 2.5. And now let's push out the boat. Let's do something fun. 1 milliliter of HA, a 1 molar solution, pKa equals 5, and we add this to 100 milliliter of water. So this one here is pH 2.5. This one here is pH 7. What is the resulting pH? I give you a couple of minutes to think about it. Please feel free to discuss that, a strategy to solve this problem with people sitting around you. How would you solve that? How would you deal with that if this came up in an exam? What would you do? He's asleep, don't wake him. How would you solve this problem? First of all, what's our volume? Say again?
101.
101. So the volume is 101 milliliter. Why? Because we add 1 milliliter of our weak acid into the 100 milliliter of water. So that's easy. Now, what about the moles of protons that we have in our new solution? Ooh, that's a bit of a bummer, because we don't know that. How can we get that? What we do know is we have our dissociation constant. So let's say we have HA, and that dissociates into H plus A minus, right? And we can write this as an equilibrium. We can write Ka equals H plus times A minus divided by HA. Well, we have to bear in mind that this is always at the end when we've dissolved it already in water. So I indicate this by end. So, do we know the concentration of this one here, of this H plus? No, we don't, because that is exactly what we want to know. Do we know the concentration of this A minus at the end? Not really. Do we know the concentration of this HA, of the undissociated acid at the end? Do we know that? No, we don't. We know what the concentration of the HA is right at the beginning. It's 1 molar. But we don't know what it is right at the end. Do we know Ka? Yeah. Yes. Oh, what is it? It is 10 to the power, you are absolutely right. Ka is 10 to the power of minus pKa. Is 10 to the minus 5. Yoo-hoo, we have at least one thing that we know from this equation. But otherwise, it is a real bugger. Okay, what can we do? Phone a friend? Ask Klapper? Ask Klapper to make a video? Cry, drink, get completely hammered. Okay, if we don't know things, we just simply call it X. So here we can write our proton concentration is X. We don't know that. What is the concentration of A minus? I like that. Did you phone a friend or did you ask Siri? Oh, that's all right, you know. It's, as long as it's not Iron Maiden. What is X? What is our A minus concentration? Sorry? It is the same as H plus, exactly. Why? Because for every H plus we get 1 A minus, don't we? So we get X times X, which is X squared. getting there. Now, do we know our end concentration of the acid? Now, I told you we don't. We only know the starting concentration. But actually, if you think about it, the end concentration of our acid is the starting concentration minus that part that has dissociated. Yeah? And what is this part that has dissociated? That's X. So we have HA start minus X. That is our end concentration. So we know our starting concentration, we know pKa and Ka. So in theory, it is straightforward, if you know a quadratic equation, how to solve this. There's a little trick to it. Because the quadratic equation gets complicated by this term here, by this HA minus X. Now, if our acid is very, very weak, then not a lot will dissociate. True? So our X will be very small. Yeah? So if the acid is very weak, we can write HA at the start minus X is probably very close to HA at the start. Because this X is only so small. Let's say we have 1,000 molecules of HA at the start. Only one molecule dissociates. So at the end we would have 999 molecules of HA, which is pretty similar to 1,000. So it's safe to say for a weak acid that we can write it like that. So that leaves us with 10 to the minus 5 equals X squared divided by our starting concentration of the acid, in this case was 1 molar. Right? Are we now able to calculate X squared or X? Yeah, it's pretty straightforward, isn't it? We can just simply bring that to that side. So we have 1 times 10 to the minus 5 equals X squared. Or X would be square root of 1 times 10 to the minus 5. And because we are dealing with a concentration, this would be mole per liter. And if we hack that into our calculator, we get 3.16 times 10 to the minus 3 mole per liter. Does it make sense? That is the concentration of protons. The concentration of protons in our weak acid. Now we use only 1 milliliter of that. How many moles of these protons do we have? Moles. We have 3.16 times 10 to the minus 3 mole per liter. And we have 1 milliliter times 1 times 10 to the minus 3 milliliter. Liter cancels out. And we end up with 3.16 times 10 to the minus 6 mole. That is in 1 milliliter. It took us a while to get there, but we got it. Okay? Happy with that? And we said we have this in 0.101 liter. That was our 101 milliliter. So if we do that, we get the concentration of the protons as 3.16 times 10 to the minus 6 mole per 0.101 liter, and that gives us 3.12 times 10 to the minus 5 mole per liter. True? Well, if he says so, trust Klapper. Never trust Klapper, by the way. He always messes up something. Now we have our concentration of protons in these 100 milliliter or 101 milliliter. So we can now calculate the pH. pH is minus log of 3.12 times 10 to the minus 5. And this gives us a pH of, does anyone want to try on the calculator?
4.5.
4.5, yes, ladies first. So the pH in this case is 4.5. So, what does that mean? We went from a pH for the acid pH HA, that was 2.5. We had water. Here the pH was 7. And when we add 1 milliliter of a 1 molar solution of this guy, we get a pH of 4.5. Would you be happy to stick your finger in a pH 4.5? Yes or yes? Pretty yes. 4.5 is all right. Actually, the skin of healthy pH, the pH of healthy skin, that's the way around. The pH of healthy skin is in a range of 5 to 6. Yeah? pH of urine is around 8.5. I told you pH of blood is 7.2. Usually the pH of the vaginal flora is around 3.5 to 5.5. So we are in physiological regions. I hope that hasn't put you off. And you are biologists, you know, you need to know these things. Are you happy with that? Yeah? Right. One last push. One last push, and then I shut up and hand over to my colleague. What is the story about buffers that I told you? I gave you this famous equation, the Henderson-Hasselbalch equation. pH equals pKa minus log of an acid divided by the conjugate concentration of the conjugate base. And it always has to be a conjugate system, acid and base. So they are conjugate. You can write this in a slightly different form. I think, Dave, you've done that in a different form. You can write that also as pKa plus log base over acid. Both forms are exactly identical mathematically. They just differ by the minus and the plus sign here and the ratio of acid to base or base to acid. It really depends on what you find easier to remember. Sort of as a mnemonic, Klapper is a positive bastard. Okay? So pKa plus base is on top. Klapper is a positive bastard. If you write that in a module evaluation, I'm absolutely fine with it because it shows me that you learned something. So please do feel free to call me a bastard. So, now the trick with a buffer is that we have a combination of an acid and its corresponding base. And usually one of them is weak. pKa, usually a weak acid in this case. So, what does that mean? What does it mean, for example, if we have exactly the same concentration of acid and base? pH equals pKa minus log acid to base. Let's say acid is 50 millimolar and the base is 50 millimolar. What do we get for the pH? And the pKa, let's say, is pKa is 7. What do we get for the pH? 7. Why? Aha! Acid to base, the ratio is 1 to 1. I can write 1 to 1, which is the same as 1. Log 1 is 0. So therefore, pH equals pKa. Okay? Happy with that? Okay, I have 50 millimolar acid and 5 millimolar base. pH equals pKa, and our pKa is 7 again. Minus log acid divided by base. Morning. Can we calculate what the pH would be in this case? So pH is 7 minus log. This was 50 millimolar divided by 5 millimolar. What does that give us? So 7 minus log, what is 50 divided by 5 is 10. 7 minus log 10 is 1 equals 6. So the pH of that would be 6. Does that actually make sense? Yes, it does, because we have more acid than we have base. More acid means lower pH. What happens if we have 5 millimolar acid and 50 millimolar base? pKa 7. What do we get? pH equals pKa minus log 5 millimolar divided by 50 millimolar. Seven minus log, what is it? 0.1. Log 0.1 is, loud? -1, exactly. So we have 7 minus -1 equals 8. Yeah? So, when we dealt with acids, pure acids, we were in a sort of a passive situation. The acid had a pH. We couldn't do anything about the pH. pH was pH. But with a buffer, we are now in control. What we can do with a buffer is that we can make combinations of the acid and the corresponding base, and then get the right pH that we want. And that is exactly what your body does all the time. It uses, for example, the acid is H2CO3, carbonic acid, and the corresponding base. What's the corresponding base to that? What's the corresponding base? It has a charge, exactly. It would be HCO3 minus, because we said the corresponding base has 1 proton less than the acid. So, in the blood, and actually this thing has a pH of 6.8. pKa, roughly. So we can say, what is the ratio of acid to base in the blood? We know that the blood has a pH of 7.2. That's the pH of the blood. Equals pKa 6.8 minus log acid over concentration of the base and we now can calculate what is the concentration, what is the ratio of the acid and the base. Well, we bring that to one side. We have log acid to base equals 6.8 minus 7.2. I just rearrange this equation. So log acid to base equals 6.8 minus 7.2, and that gives us negative 0.4. Is that right? Or have I made a big boo-boo? Hopefully not. So log acid to base equals negative 0.4. How do we get rid of the log? To the power of 10, both sides of the equation. 10 to the power of. So we have 10 to the power of log acid to base equals 10 to the power of negative 0.4. 10 to the power and log cancel each other out. So we have acid to base equals 10 to the power of negative 0.4. Can anyone do the honors? Is 0.398. Is that right? 398? Yeah. So it's roughly 0.4. Correct? Good. So our ratio acid to base equals 0.4, or I can write this without a decimal. I can write this as 4 parts of acid and 10 parts of base. Looks neater. So we know that we have less carbonic acid in the blood and more of the HCO3 minus, which is also called bicarbonate. So that's here. Where is it? This here is bicarbonate. One thing that I have forgotten or haven't told you so far is when we go back, we have an acid and the corresponding base, and the total concentration of both together, which in this case would be 55 millimolar, the sum of that is called the capacity of the buffer. Okay? So when it says the capacity of the buffer is 55 millimolar, you know that it is composed of acid and a base. How much acid and the base? We don't know at the beginning, but that really depends on the pH. Because the pH determines the ratio of acid to base. Does that make sense?